Hi everyone, welcome back. In this video, we're going to take a look at Chapter 9, Section 3, which is about de Moivre's theorem, which specifically starts to look at complex numbers in the complex plane. Alright, so we're going to start off by talking about the complex plane, which requires us to review some information about complex numbers. So complex numbers consist of a real part and an imaginary part. And as a reminder, imaginary numbers are square roots of negative numbers, and we write them all in terms of I, where I is defined as I squared equals -1. In other words, I is equal to the square root of -1. And all imaginary numbers can be expressed in terms of I. And we can do that by splitting them up. For example, the square root of -9 is equal to the square root of -1 times 9, which is equal to square root of -1 times the square root of 9, and split these up. This gives us I times 3, or you'll also see it written as 3I, or 3 in front. So we can split them up and write all imaginary numbers in terms of I by splitting them up and then writing down I, and whatever's left over we'll write down in front of I. Okay, so imaginary numbers are helpful because we can talk about square roots of negative numbers, which we aren't a part of the real number set. So we can't plot them on a real number line, for example. When looking at the complex plane, one way to start to think about this is to think of it in terms of number lines. So the real number line would just be a number line like this, where we have numbers like 0, 1, 2, -1, -2, -3. And we can pretty easily plot some numbers here. For example, we can plot any real number. 1 would be right here. 3 would be down here. But we can't plot imaginary numbers. For example, we can't plot I. There's no place to put I on the real number line. So what we can do instead is create our own number line called the imaginary number line, or create a special number line. And the imaginary number line is really similar to the real number line, kind of a copy, except instead of integers, we're going to be writing everything in terms of I. So I, 2I, 3I, I, -2I. So all the numbers are imaginary numbers because they're in terms of I, or multiplying by I. So down here, we can really easily plot I right here. Or -2I would be over to the left here, over here. So writing out these two number lines is helpful because we can combine them to create the complex plane. Okay, so the complex plane has the imaginary number line vertical and the real number line horizontal. Vertical line or axis is the imaginary axis, and the horizontal axis is the real. And the complex plane is helpful because we can start to think about complex numbers graphically. We can graph them out instead of just writing them down algebraically. -I, -2I, so on. So for example, if we have the number 2 plus 3I, that would go 2 to the right, be up. So we would be at 2, 3 on the graph. 2 plus 3I. 2, 3. If x is the real part, y is the imaginary part, or coefficient. 2 minus 3I would be 2 to the right, down 3. Extending my line a little bit, -3I. Down here we have 2 minus. We can also plot only real or only imaginary numbers, and we can do that by just filling out 0 for the other part. For example, if we wanted to plot 2, 2 is the same thing as 2 plus 0I. So that would just be right here, 2. If we wanted to plot I is the same thing as 0 plus 1I. So that would be right here. So only real or only imaginary numbers go on one of the axes, the real or imaginary axis. Okay, so Representing complex numbers graphically is interesting because we can start to combine them with what we learned in our polar unit. So thinking about points, not only in terms of x and y values, but also in terms of the distance from the origin and the angle in standard position. Before we move on to that, what I want to do first is quick just define a few common vocabulary terms that we'll be talking about for complex numbers. Okay, so the first term is called a conjugate. And when we talk about complex numbers, we'll usually be using z as a placeholder for complex numbers. You'll see it written generally as just a plus bi. The conjugate is where we take the opposite. So it's the same number, except we take the opposite imaginary part. Opposite imaginary part. So for example, if we have 2 plus 3i, the conjugate of 2 plus 3i is going to be 2 minus 3i. If we had negative 10 plus 2i, here, again, we keep the real part the same, negative 10, and then we subtract 2i. So just taking the opposite imaginary part. And when we talk about conjugates, we use the format z bar in this case. So we have a little bar on top of z, and that is the conjugate of z bar. If we had a plus bi, z bar would be a minus bi. Okay, so that's what we mean when we talk about conjugate for polar numbers. Aside about that. Okay, so looking back at the complex plane, here we can start to think about them in terms of polar coordinates, where we have r and theta, distance from the origin, and angle from standard position on our graph. Let's start off with the distance from the origin, r. We have a special word for the distance from the origin for complex numbers, and that's called the magnitude. Or another word for it is the modulus of complex numbers. And that's going to be expressed, if we have a complex number z, the magnitude or modulus is expressed as absolute value bars or vertical bars of z. So it's written in that form. And this is going to be if z is equal to a plus bi. This is going to be equal to the square root of a squared plus b squared. Another way to think of this is in terms of x and y coordinates, x squared plus y squared, where z, we just replace a with x and b with y. And that's true because we're just using the Pythagorean theorem here. If we were to pull up our number from up here, for example, 2 plus 3i, we can write this as a right triangle in quadrant 1 with side lengths 2 and 3. And then the modulus of z, or the magnitude of z, is going to be the hypotenuse. So we just square the other sides, add them up, and then take the square root. And it's always going to be a positive number because we're looking at a distance. When we write in polar form complex numbers, the r value is just equal to the magnitude of. One quick interesting note is that if we have a conjugate for a number, the magnitude of z, or r, is going to be equal to the square root of z times its conjugate, bar. And that's true because if we have a plus bi, and we multiply it by a minus bi, we end up with a squared minus b squared times I squared. And I squared is -1, so we end up with a squared plus b squared. So that same inside, a squared plus b squared. So we could also take the product of the complex number and its conjugate, put that under square root, and that tells us the magnitude of that complex number. Okay, to identify the angle theta, in other words, this angle right here, what we can do is use some of the properties we have from our polar unit. Specifically, we can use that x is equal to r cosine theta and y is equal to r sine theta. And here you can just move them around a bit. For example, you'll end up with theta is over r sine theta. Okay, so we can use that to help us find out which theta we're specifically working with. You could also use the fact that tangent of theta is equal to y over x. For this, it's important to know which quadrant it's in. Whereas if we use these two separately, these will tell us specifically if cosine is positive or negative, and if sine is positive or negative, and thus tell us the quadrant. Okay, so that's how we can find theta, the angle from standard position. Here we looked at complex numbers on a plane. Talked about from the plane, using a triangle, how we can find r and theta. Another way to find these values or to write these values down is to write down complex numbers in polar form. So we're going to look at the polar form of complex numbers. If we have a complex number z, we can rewrite that as r times cosine theta plus I sine theta. And that's true because we can use the two equations up here and just substitute them in. If e is equal to x plus yi, just replace x with cosine theta, r cosine theta, replace y with r sine theta, and then we can factor out the r to get r in front. R times cosine theta plus I sine theta. That's going to be the polar form of complex numbers. This is helpful in a few different ways. If you're just given the angle and the distance from the origin, you can really easily write out the complex number in this form. It also helps us with working with complex numbers in this form because we have a couple of rules that'll help us out. And just a quick note here, when we talk about r, we do talk about the magnitude of z, so it's distance from the origin. Okay, so this is helpful first because when we multiply or divide complex numbers, especially if we're given them in polar form, we can use a shortcut here. And that's that if we have two complex numbers where z1 has a magnitude of r1 and a theta, angle and standard position of theta 1, z2 is denoted as r2 and theta 2. So the magnitude and the angle for z2. If we have two complex numbers and we multiply them, z1 times 2, we can actually write that out as just r1 times r2, and then in parentheses times cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And we're not going to go over the proof for this specifically, but it is an interesting proof. It's on the bottom of 587. And what it does is it uses the sum formulas that we learned when we talked about trig identities, and it substitutes what they're equal to, and it kind of, you can work from the bottom up using that substitution to rewrite it as if we were to just write out r1 times cosine theta plus I times r2, so on. Okay, so when we multiply complex numbers, we can rewrite it like that. If we look at the quotient, we also have a very similar simple result. Here we have r1 divided by r2 times cosine of theta 1 minus theta 2 plus I sine theta 1 theta 2. Where again, theta 1 r1 are the is the angle and the magnitude of the complex number in the numerator specifically. Okay, so in this video, we took a look at complex numbers. We did a quick review of what complex numbers are and what imaginary numbers are. We created the complex plane and talked about how to start to think about complex numbers graphically. We also connected complex numbers with polar forms of graphing using r and theta. We talked about the conjugate of complex numbers, and then finally we ended by writing down the polar form of complex numbers.